the simplest matrix I am going to consider written, oh my, no. It is written here, just you have X, it's M by N random matrix, and T is not random, or if random, independent on X, and XT was just transposed. And our goal to study eigenvalues of this matrix at the limit of large Mn and asymptotically proportional. So this is the goal of lectures. I'll try to explain how you can see this asymptotic form. And here is the outline of my lectures. As far as it stands, there will be 3 lectures. The first part of the first lecture will be a kind of tutorials on 3 domains which I am going to use: linear algebra, analysis, and probability. But it is mostly basic notions and just notations which I'm going to use. The second main part is, as I said already, this is eigenvalue distribution of large sample covariance matrices. And it consists of several, this is a kind of chapter, and the sections will be, first it will be proven that the distribution is becoming non-random in the large size limit. And second, and mostly technical, what is this explicitly, what is this distribution, how does it look? And the third part, if time will allow, I'm not sure, as I mentioned, there are many applications. I would like to present some of them, which is a kind of quite intriguing because it deals with black holes, etc., etc. But we'll see if you will have time. Well, let me start from I believe that mostly written on that slide you know already, but just I repeat to establish notation. So we will deal with n by n Hermitian or real symmetric random matrices. So it is here it's just how will I write the entries. This is just either Hermitian transpose or if matrix is real symmetric transposed. And here is already the important fact that I am going to use many times, that if you have not necessarily, by the way, a Hermitian matrix, but entries are bounded from below by the norm of this matrix. I do not give a definition of norm. I believe that everybody knows. So the eigenvalues will be of these matrices will be real, and their collection is called a spectrum, and it will be the notation like that. Eigenvectors, they supposed to be orthonormal. This is Hermitian, but I will deal mostly with real symmetric matrices, which is just real version of Hermitian ones. Yes. Third thing that I'm going to mention, it's already less trivial, less known, but it will be quite important in what follows. This is called rank 1 matrices or rank 1 operators. You have 2 vectors belonging to your space, and you introduce the linear operator, which acts on any W of your space by that formula. And it is easy to see that if I would like to write its matrix, so the matrix, the entry of the matrix will be given by this product. A particular case of rank 1 operator, then these 2 vectors are equal and their norm is 1. It's called orthogonal projection, and it's Hermitian. This matrix is not necessarily rank 1 matrix not necessarily Hermitian or real symmetric, but orthogonal projection is Hermitian. And okay, the square is 1, and the entries in full correspondence with this formula, the entries are just products of the vector on which the project made a projection. And of course, the trace is 1, and it is just the consequence that the projection is rank 1 operator. And quite important, I would say, cornerstone of spectral theory of Hermitian matrices, and by the way, Hermitian operators, is the spectral theorem according to which any Hermitian matrix can be written in that form. So the linear combination of projections on eigenvectors, coefficients, eigenvalues, and this allows us immediately define any function roughly of the matrix. Just to take a function, real, define it on a real axis. Excuse me. And the values might be even complex, and you write the function of the matrix. What is it? It's just the same eigenvalues, eigenvectors, by eigenvalues are functions of the eigenvalues of matrix M. And the formula again will be used many times. The trace of the matrix, by definition, is just the sum of diagonal entries of your matrix, but by spectral theorem, by using the fact that eigenvectors are orthonormalized, you can easily prove that it is just the sum of eigenvalues. Well, it is more or less known things. Now I will introduce the important object of spectral theory. Excuse me. Which called the resolvent. I believe that is it well seen because the top line in my computer is almost vanishing.
It's very well seen. Okay.
Okay, so the resolvent is just the special function of the matrix written over here. With, in general, you take Z complex not to have this matrix well defined because you see it is in denominator. But we know for sure that if matrix Hermitian, there is no eigenvalues outside of real axis, then you are surely the resolvent for any Hermitian matrix is well defined for non-real Z's. And there is very simple formula which relates to resolvents of two matrices. You have two Hermitian matrices, then you can write this for this simple algebra. Okay, it is just difference of two inverse powers, but because of usually these matrices do not compute, you have to write in the appropriate order this thing. And by one thing about resolvent, second things about resolvent. So by spectral theorem, it can be written in that form. And it follows immediately from this formula, from spectral theorem, that the norm of any of the resolvent of any Hermitian matrix is bounded by this quantity. So it is if you're out. Okay, general definitions that you have to be outside of the spectrum. Okay, to be sure, you can take always like Z, but assume that our matrix M is positive definite, then the resolvent is well defined even for real spectral parameter, but negative ones. Yeah. Well, and now let me show you maybe the main thing. Oh, no. Excuse me. The main.
Do anyone here as well?
I see almost nothing. I hear the sound is very weak. I do not hear, unfortunately. Hello. There is no. Is there a question?
You have.
Anya, is there a question? I hear nothing.
Презентация есть на телефоне.
You can see the slide.
Okay, sorry, we decided our lot of questions. So you will have presentations on phones if you don't see it.
Could I continue?
Yeah. Thank you.
Okay, unfortunately, I can't answer any question because I hear almost nothing. I don't know what is going on. Well, so we have this situation, and now I I come to a quite important formula, which will be quite instrumental in my talk. If you have two matrices, any matrices, and you add to the matrix A, you add just orthogonal projection times real number tau, then you can write explicit formula. I stress explicit formula for the resolvent. Excuse me, there is no C here. So the matrix, the resolvent of B, which is the sum of two, can be expressed explicitly, while the resolvent of unperturbed matrix A and the perturbation, what is a perturbation? It is just the real number tau and the vector of our space U. And just given this formula, which I believe it will be explained on your exercises, we can easily compute the trace of the difference of two matrices, perturbed one and unperturbed. And you see, this is quite nice and explicit expression for the difference, which is, by the way, it's a unique case when you may know that if you have eigenvalues of two matrices and you make a sum of this matrix, so it is quite hard to find eigenvalues. But here it's just practically unique case when it is possible. Well, and so we have this formula. What is a normalized? I use normalized traces. I make the trace of matrix, or this in this case of resolvent divided by the size of matrix. And then we see this formula and its particular case. So this is general thing, but of course there is a denominator, which you have to be sure it is not zero. But if, for example, both matrices are positive definite in the number tau is not negative, then you can easily compute the difference, bound the difference by quite nice in simple expression. And I will use this heavily in what follows. And just looking at that formula, you can derive quite important properties of eigenvalues of B and I, which is written here. If we denote the eigenvalues of unperturbed A like that and perturbed B like that, so it turns out that they are intermittent in the sense that, okay, they follow one after another. It's written here. It's called intermittency. So if tau is positive, and from here you can easily derive that if you take any interval on the real axis, spectral axis, and you have a number of eigenvalues of the unperturbed one and perturbed, the difference is bounded always, doesn't matter what are matrices, what is a space. Even in infinite dimensional case, the difference is not more than one. And excuse me for very primitive picture, it is explanation why it is like that. So look, what are eigenvalues of your perturbed matrix? It is easily seen from that formula. You can easily see that if U is not a vector, eigenvector of A, then all eigenvalues are simple, that means the multiplicity of each is one, then no eigenvalues of A are eigenvalues of B. And new eigenvalues of B, perturbed matrix, they are poles, they are zeros of this denominator. So if we solve this equation as a function of, okay, what do? We write the equation which determine new eigenvalues, the lambda, so it is function of lambda. This is a graph because this is GE, matrix A. So this function has poles at the eigenvalues of the unperturbed matrix A. Then you write this equation, you solve it numerically, graphically, and you see the eigenvalues are also in between. And from that, you immediately derive the formula, which I am going to use heavily also, that if you do rank 1 perturbation of any Hermitian matrix, the number of eigenvalues which falls in any interval differs mostly by 1. Well, and now let me pass to certain facts of analysis which I am going to use. First of all, these are P measures. Just P its probability measures. This is definition. Any non-negative measure such that its total mass is 1, and we are going to consider only measures supported on a positive semi-axis. So I assume that 1, not R, but R plus. And the important notion is if you have a collection of P measures, we say that this collection is tight if the tails, the mass of the measure, which is close to infinity, is bounded uniformly in the collection. This will also be used. And now the important notion of weak convergence of measures. So we say that two measures are weak convergent if there is this convergence for any delta excluding infinite one. This an equivalent definition you can check. It's good, by the way, good exercise. That this definition is equivalent to that definition. That integrals from the measure of your sequence and the function which is continuous and bounded at infinity, you can make the limiting transition under sign of integral. And the last but also important fact is that you have infinite collections of tight P measures, then there is always a subsequence that converges weakly to tight measure. It could be many limits, but at least one limit always exists. So, and one more facts from analysis is the following. Given a P measure, I can write this integral, which is well defined for all z that do not belong to the support of the, on the support of the measure. And again, you have quite general bound. Doesn't matter your operator random, not random. The only thing that important is self-Hermitian, and you have a bound that your Stichiast, it's called Stichiast transform. It is bounded by, again, by the distance of the z, of the parameter or variable, distance from the support. And there is quite important inversion formula by these authors that allows given, so this formula determines f provides that you know nu. Now I would like to find nu knowing f, and this formula is determined nu. So we have this is one-to-one correspondence between Stichiast transform between function of complex variables and P measures. And it turns out that if you require that if you just looking from the side of complex analysis, you have a function of complex variables such that the product of imaginary part on imaginary part of z is positive, and then then this one-to-one correspondence is continuous. You can do the limit in both formulas. Nu for the measure sequence of measures, you can do the weak limit, and here you can do as for the Stichiast transforms, you can do the limit on any compact set of complex planes that does not intersect the spectrum. And we will go in, since we are going to use the measures whose support is just positive semi-axis, it suffices to study there is a continuity if you just if you just know that your Stichiast transform of your sequence converges on any interval of negative, it is mistake, R minus. Correct. T is positive, a minus T is negative. So, and then if you have if you have this one-to-one correspondence, if you have a sequence of weakly convergent measures, then the limiting measure exists and had this property. And the opposite, if you have a sequence of Fourier, Stichiast transform, and you know the convergence on any interval, and you know that limiting transform possess this property, then then the continuous correspondence is the case. Okay, if you would, it's very interesting subject. You can refer to the book of our Kosisy and Naumilic Ahiezer by looking at a very nice book in which all these things are explained. Well, and now the last thing is probability, some facts of probabilities that I'm going to use. Okay, I'm going to consider an infinite sequence of identical, independent, identically distributed random variables. Okay, that means that they have the same probability law, and I denote the expectation with respect to infinite product of measures, well defined, and I will assume that I normalize. Okay, I denote the expectation of all xi mu. My normalization is called, without loss of generality, that the square, the expectation of square is 1, and I will assume sometimes, not always, excuse me, that the finite moment is finite. And then I would like to consider quadratic form. Given a matrix A, not necessarily even n by n, even not necessarily Hermitian, I write this quadratic form with respect to random vector, which is my axis, not just centered. It's called in probability centered random variable. If you subtract expectation times the square root of n, okay, minus, yes. And then the two assertions which I leave for the exercises is the following. By using the fact that you have this expectation, it's easy to prove that the expectation of quadratic form is just the normalized trace of matrix A. Yes, and it is almost trivial, a bit less trivial, to prove that the expectation of the absolute value squared is written here. This is why I need the fourth moment, you see? And just from that, you find the variance. Variance, by definition, is the expectation of square minus square of expectation. And you can easily find this bound by using what you do here. You see, it's everywhere a square. You bound a square, what is a trace? It is sum of a squared jj, yes? You bound any entry of A by norm, you'll get this bound with a norm depending on A and the coefficient depending on xy's. Well, and now two basic facts of probability theory, which called law of large numbers. In fact, there are two laws. First is called weak, or just law of large numbers. And this is assertion, as I said, if you form arithmetic mean of your random variables, the probability that this arithmetic mean is differs from the expectation of mu on a little amount epsilon tends to 0. Epsilon is fixed but arbitrarily small, n to infinity, and it's called, we say that arithmetic mean converges to the expectation, the real mean in probability. There is a stronger assertion that this limit exists for almost every realization. What is the realization of this axis? Just the infinite sequence of values of our random variables. And in that case, we say that the convergence is with probability 1. Yes, and the proof, okay, here I'll need below. You have to compute the two moments. Let's compute the second moment of centered of the arithmetic mean, and it is easy. Okay, it's I already said that the second moment is 1, but in my previous version it was sigma squared. So replaced your sigma squared by 1. And then you use the Chebyshev inequality and you'll get this statement. But a bit more tricky, for the strong law of large numbers, you have to compute the fourth moment. And you can easily you see that this moment is decays as 1 over n square, unlike here 1 over n. And you can use the very nice and simple statement of probability, which calls Borel-Cantelli lemma. If you have a random variables, in our case this, the probability to have non-zero values is bounded by something, then and if this probability decays, so what do? You write that, you replace for p equal 4, you replace that by the 1 over n square, then the series of these quantities converges, and it is Borel-Cantelli, and you get the strong law of large numbers. And the last facts, this is a good examples. Take random variables just independent, identically distributed, yes. No, I know. Yeah. No, nothing. Excuse me. One more fact which I need, the following. Okay, excuse me. Yes, this is a elementary things you find in any book on probability theory. A more sophisticated fact which is based on the same ideas, but a bit delicate applications is the following. Assume that we have a random variables again, independent, identically distributed. We have a function of m variables, and we form this random variable, which is called statistics. Yes, and then you define the following. Now we use crucially the fact that the random variables are independent. We take this function, this random variable little phi, and we make the expectation with respect only first alpha random variables of here, yes? And we denoted phi alpha, phi naught, it is our random variable, phi m, expectation over all size, this is just expectation. And now we write the things which is called telescopic, yeah? You write this deviation of your random variable from its expectation as you write what is it is phi, then you subtract phi 1 plus phi 1, etc. And you can write it's just identity because delta alpha is defined in that way, yes? Yes, and now let's make second moment of this equality. Okay, so what I do, I apply to this identity, I apply expectation squared. And of course, this is written like that. And the miracle, so miracle that the sum, the second sum is 0, because if alpha is strictly less than beta, but alpha equal beta there here, then just you have one more expectation with respect to, okay, for example, you have alpha minus 1 and beta equal alpha. Then there is one, because of subtraction, there is one expectation that make 0 from that. Okay, I propose it's very good exercise to convince yourself that this sum is 0, and it is a miracle because you take a square. So here is a double sum, but here is just one sum. So roughly speaking, your variance is always provided that every term in this sum is bounded. It's order m, but not m square, as you would see, just trivially squaring of this identity. And even more miracle, this is a good example. So you take your statistic, your phi, just a sum, and you see that in that case, we return to the case standard situation by which we prove the law of large numbers, yes? And now a bit more work. So you can do the same trick with the fourth moment. And okay, this is already a bit involved combinatorial calculations, and I leave it to you, or you can look at any good book on probability theory. So the bound from below is given again. So the fourth moment, it is you have the sum with respect to 4 indices. So roughly, naively, this sum of the order m4s. But because you do expectation, your sum is just m squared. Yes. And important remark that here I did everything by assuming that xi's are just real valued eigen random variables, but they could be even multi-component. It could be a random vector, and you can easily verify that this argument works as well. Well, and now, stop. I don't understand what is going on. I don't understand. Okay. Now I am passing to the subject of my talk. We will deal. Okay. Consider the infinite table. You see, this just semi-infinite formal metric. Just I even do not use the word metric. Just a table collection of random variables, real valued, independent, and indexed by 2 indices, alpha and j. Yes. And I assume that the expectation of them is 0, expectation square is 1, and now I take the upper left corner of the size m over n, rectangular corner, and this is my matrix that I am going to consider. Excuse me for a bit clumsy notations, but I will not use them everywhere, just at the beginning. So we have this rectangular matrix, which we denote in that way. X upper index mn. And okay, this will be a part of construction of my matrix, which I am going to study. No. And one more matrix, just matrix Rm, not random, real symmetric and diagonal. And its diagonal entries we call tau alpha. And since we assume that Rm is positive definite, of course, tau alpha, they are non-negative. Yes. And we introduce an important things which will appear in many instances below. This is normalized counting measure of these taus or eigenvalues of our matrix R. So what is it? This is a measure. If you ask me if you take an interval of real axis and you'll ask me what is the value of this measure corresponding to that interval, it will be the number of taus falling in that interval divided by the total number. And we will assume that this is in fact the sequence of matrices, yes, for any m. And I will assume that this normalized counting measure converges weakly to a certain limit, which I will denote nu r. Yes. And now here is my matrix that I am going to study. So I will study the matrix M, n by n matrix, positive definite, which is defined in that way. I take this rectangular matrix, its transpose, then R, and then the matrix itself. It's easy to check that it is not negative. And I introduce these eigenvalues of this matrix, I denote lambda s, they are n. I assume, by the way, the conventions that I had to tell at the beginning, that if some eigenvalues coincide, I view them as I count them counting multiplicity by different numbers. So and since we are dealing with random matrices, so generically, of course, they do not coincide. So it is just justified convention. So I view eigenvalues, I count them, taking into account multiplicity, and I introduce the normalized counting measure of eigenvalues, and my goal is written here in the red. I would like to prove two facts. No. Two facts. First, I would like to prove that under conditions that I said, that matrix is, there is a mistake. Excuse me, there should be n minus 1 in front of this matrix. Here there is n minus 1 leg here. So I would like to prove that this normalized counting measure converges with probability 1 to non-random limit. Yes, what are conditions of the limiting process? Because my matrix depends on two indices, so it will be m to infinity, n to infinity, but the iteration is asymptotically proportional and tends to a number c, which is non-negative number and not infinite. So this is the first problem. And second, find, okay, this is just a proof of I have to prove the existence of the limit, not necessarily to prove it, but I am quite interested in prove as much as possible explicit, to find as much as possible explicit form of nu m. So these are problems that I'm going to discuss. This is a problem that I'm going to discuss in the rest of the talk lectures. And this is a theorem which gives the answer on the it's not optimal solution, but quite good. Okay, we assume that our matrix as above, but I repeat, excuse me, here so just in front of this right hand side, there should be 1 over n. So I assume additionally that the entries of x, let me remind you, the entries of x, their expectation of 0, the second moment is 1. Now I assume additionally that the fourth moment is found. It is just to make the proof simpler. You can read off of this condition. And second, also technical, to make the proof simpler, I assume that this number tau alpha, which are in fact eigenvalues of this central matrix R, I assume that the arithmetic mean is bounded uniformly in M. And under this condition, the claim is that I can prove the both statements. I can prove that nu mn converges to a certain limit with probability 1. The limit is not random, nu m. And if I write its CTS transform f, then it satisfies this equation. And the equation, you see, it is functional equation because f is here and f is here under the integral sign inverse. So it is nonlinear functional equation, but nevertheless it is okay. It is if you want, it is explicit form modulo this condition, and it's by the way the good point that it depends on the problem to which extent you can write the result of your theorem of your calculation in explicit form. It is impossible in general, for general case, for general R, to find matrix nu explicit. Is that just few examples? I'll show one of them, simplest one. But if you pass from nu to f, from the measure to its CTS transform, you are able to write, so to say, explicit equation. And in a way, this is a good job because look, we started from infinite number of parameters. There is infinite number of x's, infinite number of taus, and nevertheless, you ended up with just one single equation. Okay, in my opinion, it's not so bad. Well, and how much I have time still? Okay, 15 minutes. Well, let's proceed to solving this problem. And the first thing,
Sorry, we have a question, and now it will be asked.
Okay, can you hear me?
okay, just a little.
Yeah, just a small question. What are conditions we impose on tau alpha?
I thought the one condition is a condition to i's of the theorem, but it is not all. Much stronger condition is here. You see, the eigenvalue, the normalized counting measure of tau alpha has to converge to a certain limit.
So this is also assumption, right?
Sorry?
It is also our assumption.
Yes, there are two assumptions. I have assumptions. No, So for tau I, two conditions, that one and that one. And why, you can ask me why I wrote them in different places. Because as I said, the conditions of the theorem written here, they are just, I wrote them to make the proof simple for my lecture. In fact, none of these two conditions is necessary. The theorem is valid for under conditions, as I said, here, this condition, okay, xi, ji independent, identically distributed, normalized like Z, matrix R is such that this measure converges to the limit, and it's so. And you'll get the theorem still holds. But the proof is much more technical. This is why I just, okay, I added this condition to make proof possible to explain in 1-2 lectures.
Okay, thank you.
Yes? Well, and this is a remark, by the way, answering your question. So we can consider much more general metrics written here in which we can add the matrix M naught, assuming do not assume neither condition I nor condition 2 I's, but just assuming so no fourth moment, and we only assume that the eigenvalue normalized counting measure of eigenvalues of M naught and R converges to a certain limit, and then we have the same assertion that the eigenvalue normalized counting measure of Mn converges to non-random limit, and its TTS transform can be found from the similar but a bit more complex equation written here. And you have this equation, you have to look for the solution of this equation in the class of function of complex variables satisfying the condition, that one and that one. So, in that class, the solution is unique, and it is precisely, this solution is a TTS transform of our limiting measure, nu m. Yes. And by the way, the interesting point that I will not discuss at all, but just mention, look, what do we have here? We have on input, you have two measures. You have random matrix and two measures, nu R and nu M naught. That one and that one. And taking this, forget about randomness. You have this equation. The equation written, you know the nu R and M naught, and knowing M naught, you write its CTS transform, and this equation determine new CTS transform and the measure nu M. So you have a roughly binary operation. You have measure M naught in R, and you have operation which I denote in this funny way, new measure, and you can study this operation, and there are several contexts in this. This point of view is quite useful and quite efficient, and this branch of I would say functional analysis now is called free probability. Well, let's pass to so we will start. I have still just 10 minutes to prove this assertion.
You have 10 minutes plus 15 for discussions, so you can
Sorry?
You have 10 minutes plus 15 for discussions, so you have 20.
15? I told that the
10 plus 15, so it's 25.
Okay, I have 5 minutes, yes?
Plus questions.
I have 5 minutes. Okay, it's just to formulate this assertion. So we are starting to prove the theorem, and the first assertion that I'm going to prove, and it's of certain interest in itself, that assumes that we have the matrix that was written above, yes, and its eigenvalue normalized counting measure. This is our matrix. Now you see here is n minus 1. It's correct. And now denote by this new bar the expectation of that measure. Yes. And my assertion is the following. You have the measure nu m is random because the matrix is random, and measure it is just a number of eigenvalues falling in a certain interval, so it is random, yes? And so I would like, I take the expectation of this measure, yes? And now I take the difference between the measure itself and its expectation. I claim that this difference, it's again random variable, so it converges with probability 1 to 0. So at the measure, you can say that we do not know whether the limit of whether we just know that difference of two measures tends to 0. If we will be able, upon proving this assertion, to find the limit of the expectation, we are done. The two problems that I formulated in the previous slide here, they will be solved. So it is an important part of on the way to solve the problem. I would like to prove that the difference of the normalized counting measure of random matrix Mn, which is determined by this expression, and between this measure and x expectations tend to 0. And this is why you can say that the fluctuations, we do not know whether the limit of expectation exists, but we know that this random measure nu n fluctuates less and less when size of matrix tends to infinity. Well, I believe that I'll finish on that point.